This time out, we're going to focus on the Blake-256 algorithm being used in our transaction hashing process. Our starting point consists of the initial hashing values H0 to H7, the hashing constants C0 to CF, and our first transaction block of 16 word messages M0 to M15. Each of our transaction blocks gets processed sequentially, starting with block 1 through to block 3. Each block undergoes 14 rounds of processing, with each round containing 8 mixing functions. This process is then repeated for each transaction block, using the final state of the previous block as the starting point for the next block. The G function is a core component of the Blake-256 cryptographic hash algorithm, serving as a quarter-round operation that mixes 4 32-bit state variables with message words and constants. The function takes 8 different input parameters each time it's run, and runs 8 times per round. That's 112 times for each transaction block. The 8 variables being passed into this function are A, B, C, D. These 4 32-bit state variables forming a quarter of the algorithm's internal state. MX, MY are the 2 message words from the input being hashed. And CX, CY are the 2 constant values used for cryptographic security. The function performs 4 sequential mixing steps, each combining addition, XOR operations, and bit rotations. First mix. A is updated by adding B and the XOR of message word MX with constant CX. Then D is updated by XORing with the new A value and rotating right by 16 bits. Second mix, C is updated by adding the new D value. Then B is updated by XORing with the new C and rotating right by 12 bits. Third mix. Similar to step 1, but using message word MY and constant CY. The D value rotates by 8 bits this time. Fourth mix. Final update to C and B, with B rotating by 7 bits. The calling code shows how the G function is used in 2 phases during each round. The column operations. Mix values vertically in the 4x4 state matrix. And the diagonal operations. Mix values diagonally for diffusion. Each call processes different combinations of state variables, message words, and constants, ensuring thorough mixing of all input data. The rotation amounts, 16, 12, 8, 7, are carefully chosen to provide optimal cryptographic diffusion while maintaining efficiency on 32-bit processors. The G-step function is repeated 8 times for each of the 14 rounds. In each round, the M and C values are paired and then passed into the function using different permutations. For instance, in round 1, the values are sequenced in order from 0 to 15. There are 10 distinct permutations used for rounds 1 to 10. Rounds 11 to 14 are repeats of the first 4 rounds. The permutations being passed into our G-step function continues to update our 4x4 matrix until we process step 8 of round 14. This concludes the processing for our first message block. Before we can move on to processing the next block, we must run a final folding calculation on these outputs. This will form the initial state for the next block. The folding calculation established 2 new H0 to H7 values. The C0 to CF values remain the same, or as the name applies, are constant. Once the initial state for block 2 has been established, we then repeat the 14 rounds of processing. This time with the new hash values H0 to H7 and the next block's word messages M0 to M15. Depending on how many blocks you have for your transaction, the process of 14 rounds of compression, followed by folding the N values to start the next block, will repeat. In our case, at the end of block 2, we have to do this process one last time for block 3. Fold the final values to create the new H0 to H7, which creates the initial state for block 3. Once we get to round 14, step 8 of block 3, this final folding value becomes our transaction hash. Throughout this process, we've demonstrated how the initial values and transaction data is used to produce an unchangeable deterministic 64-character representation of our transaction data. A truly unique and fully reproducible identifier for our transaction, where if even a single value is changed, you end up with an entirely different transaction hash.